all, I'm Samender Singh. My department is Computer Science and Engineering in the college, Akgec Engineering College. My subject is Artificial Intelligence, code KDS 071, and my topic is Operator Splitting Method. So in today's session, I will cover what is operator splitting method. After that, I will cover numerical solving method, that is Lagrangian multiplier method. After that, we will discuss some numerical related to this one. So start with operator splitting method. It is a method, or we can say numerical techniques that are used to solve partial differential equation. Generally, partial differential equations are very simple that can be solved very easy manner. But sometimes it will, or we can say for complex or partial differential equation, we need some special methods. Operator splitting method is one of them. So in which we are breaking down the problems into simpler subproblems that can be solved separately and then combined to obtain the overall solution of the given complex PDE, या partial differential equation. These methods are particularly useful for complex PDE that are difficult to solve directly. And the basic idea behind operator splitting method is to split the differential operator of the PDE into simpler operators that can be solved individually or more easily. We can say, suppose we have complex PDE, so we can break down these PDE into simpler PDE. PDE1, then PDE2, then PDE3, then PDE4, or in a number of simpler partial differential equations. After that, we solve these one. As these are very simple, so we can solve this in a very easy manner. So after getting solution of each one, solution of first one, then solution of second one, then solution of nth one. And after getting solution of all the simpler partial differential equation, we merge these solutions to make the overall solution of the given complex partial differential equation. So the journal procedure involved in the following steps. We have basic 3 steps. So as a first step, we are splitting the operators. So every partial differential equations have a number of operators. So in the first step, we need to recognize these operators, and then we will split these operators. The differential operators in the partial differential equation is split into simpler part, just like if the partial differential equation contain multiple differential operator, each representing different physical process, these can be separated. So as a first step, we need to separate out these number of operators. This is our first step. In the second step, we have number of simpler partial differential equations. Now we need to solve each one by one. So each simplified subproblems obtained from the split is solved independently. These simpler problems are often ordinary differential equations or simpler partial differential equations that can be solved using known techniques or specialized method. This is our second step for solving this. Then after getting solution of each simpler partial differential equation, then we will combine the solutions, or we can say we can combine the number of solutions. And these solutions from the individual subproblems are then combined to obtain an approximation to the solution of the original complex partial differential equation. This is very similar to divide and conquer approach. an example where we are using operator splitting method. So it is frequently used for reaction diffusion equations in which we have number of operators, a class of PD that describe the dynamics of chemical reactions combined with the movement of substances through diffusion. In these cases, the PD is often split into two parts, one handling the reaction, or we can say chemical kinetics, and the other handling the diffusion. So this is very common example of operator splitting method. Each part is then solved separately, usually with specialized techniques before combining the solution. So it is a very common example. We have to list this one. Now the second topic is augmenting Lagrangian method. It is very important as far as we discuss our syllabus. So what is this? These are the optimization techniques used to solve constant optimization problems. They involve adding penalty terms to the objective functions to handle constants and using a Lagrangian multiplier approach to iteratively find solutions. Here are common examples of their applications. So it is also a very common approach through which we optimize the techniques. Again, in the problem we have number of constraints. So we can find the optimal solution of that problem. These are some common problems that can be solved by means of augmented Lagrangian method. The first problem is optimal control problem. That is in the field of optimal control, such as in robotics or engineering. Very hot area in nowadays. Augmented Lagrangian method are used to solve problems where a system's dynamics needs to be optimized while adhering to certain constraints. For instance, in robotics, the motion planning problems might involve minimizing energy consumption. So this is our first constraint, that is minimizing the energy consumption while following a specified path and avoiding obstacles. Augmented Lagrangian methods can handle these constraints effectively by penalizing violation of the constraint and iteratively adjusting the Lagrangian multiplier. So by means of Lagrangian methods we can solve optimal control problems that are frequently used in robotics. So this is our next example where we are using this optimization technique. Second is image processing. In research area, it is very common field. So image processing and inverse problem, various optimization problem arises, just like image reconstructions or denoising while satisfying certain constraints. Augmenting Lagrangian methods can be applied to solve these problems. So this is our first requirement through which we can solve this one. Augmented Lagrangian methods can be applied to solve these problems. For instance, in medical imaging, reconstruction images from incomplete or noisy data while preserving certain features like shape, edges, can be formulated as a constant optimization problem where the constants are enforced using the augmented Lagrangian approach. So this is second field where we are using optimization techniques. Now third is structural optimization. Augmenting Lagrangian methods are widely used in structure optimization to find the optimal design of the structures while considering various constraints such as stress limitations, weight requirement. So these are our constraints given. First is stress limitation, then weight requirement or geometric constraint. Just like in civil engineering or aerospace design, where designing structures that must withstand a specific load while being light where augmented Lagrangian method can be employed to optimize the structure, shape, or material distribution adhering to constraint or stress and deformation. So you can see there are number of constants through which we need to find optimization. So these type problems can be solved by augmenting Lagrangian methods. Now our next topic is Lagrangian multiplier. So Lagrangian multiplier method is a powerful technique used to solve constraint optimization problem both in calculus and in optimization theory. It allows us to find extrema of a function subject to one or more constraints. So again we need to find optimal solution of a given problem having number of constants, just like this one. Suppose we have given an optimization problem with an objective function. So this is our objective function f having number of variables f1, x1, x2 up to xn. So we have n number of variables and we need to maximize or minimize. So we are going to optimize the given function subject to m equality constant. So we have given number of constants just like this one gi. So we can say g1, g2, z3 up to zm. So we may have m number of constants, possibly addition inequality constant. So in this particular problem we have number of constants. They may be equality or non-equality constants. So there are number of problems that can be solved by using Lagrangian multiplier method. First, we have given function fxy and we have given one constant, that is x2 plus y2 equal 1. So as a step 1, we need to find number of variable of the given function. So clearly we can see here we have two variables xy. So two variables is there. This is our first step. Now need to find number of constants. So in the problem 1 we have one constant, that is x2. Constant is x square plus y square equal 1. One constant. So number of constant equal to number of multiplier constant. So in this particular problem we have one constant, so we need to find one Lagrangian multiplier. So start. Now second step, we need to take derivative of the given function, that is del f with respect to first variable. We have two variable x and y. So first we need to derive with respect to first one, that is df upon dx will be equal to constant, or we can say this is our constant, that is gf. So we need to take derivative of this constant with respect to same variable, and then we are multiplying the constant, Lagrangian multiplier constant. So this is second step. So after solving this one, so this is del xy upon del x equal to del upon del x square plus y square plus 1 or minus 1. So this is equal to y equal to 2x lambda. What is lambda here? Lambda is a Lagrangian multiplier. So since in this problem we have one constant, so we need only one multiplier. So again equating this one, this is our second equation. Again doing the same step with respect to second variable, that is d del f upon del y equal to del of dx upon del y into lambda. This is del f upon del y will be equal to x, and after getting derivation of this constant with respect to y, we are getting 2x 2y lambda. So this is our second equation. On solving these two equations, we are getting, we can say x y equal to x square lambda, and in the same way x y equal to y square lambda. Both are having the same value, so we can say 2x square lambda equal to 2y square lambda. Again cancel this one, lambda to lambda, that is x square equal to y square. This is our first thing that we need to, that is x square equal to y square. So in this way we can find some points, or we can say some relative point through which we can find the minimum or maximum point. After getting x square equal to y square, on putting these values in the function, we are getting x square plus x square equal to 1, or we can say 2x square is equal to 1, x square is equal to 1 upon 2, or we can say x equal to 1 upon plus minus under root 2. So these are two values of x. In the same way, we can find plus minus 1 upon under root 2. These are two y values. So we have 4 points or 4 relative points. That is p1 may be equal to x first value, that is 1 upon root 2, comma 1 upon root 2. This is first point. In the same way, we can find second point, that is 1 upon root 2 minus 1 upon root 2. Then third point, that is minus 1 upon root 2, 1 upon root 2. And in the ways, fourth point, minus 1 upon root 2, and that is minus 1 upon root 2. So this is how we are getting 4 points. Now we need to find the maximum or minimum value. So we can put these 4 values, or we can say these 4 point values to the given objective function. So when we give these point value to function xy, so it will become x value is 1 upon root 2, then 1 upon root 2, it will be 1 upon 2. This is our first value. In the same way, we are getting values just like 1 by 2, minus 1 by 2, or 1 by 2. So we have two value that is equal, or we can say half, positive half. So on this point we are getting maximum value, and on these 2 points we are getting minimum value. So this is how we are getting maximum or minimum values of the given function. So this is how we are solving first problem. In the same way, we are able to find the second one. Now we can solve second problem. Problem 2, in which we have a function that having 3 variables, that is x, y, and z, and a constant that is x square plus y square plus z square equal to 1. So let's solve this one. So we have a function that is f x y z equal to x y z, and a constant that is x square plus y square plus z square equal to 1. So as a step 1, we need to find the number of variables. So in this particular problem, we have 3 different variables, that is x, y, and z. After that, we will find derivative of with respect to first function, that is yz, and derivative of the constant function with respect to first and taking lambda. So this is our 2x lambda. On equating this one, yz equal to 2x lambda. This is equation number 1. And in the same way, we are able to find xz equal to, again, y lambda. And in the same way, we are able to find x, yz, xz, or we can say xz, yz, xy, 2z lambda. So these are 3 values. We have 3 different values, and we need to find the values of x1, y, and z. So on equating all is x, y, z. So this is x square. On equating each one, we are getting 2x square lambda equal to 2y square lambda. Cancel out these terms. We are getting x square equal to y square equal to z square. So this is our first term. On equating these things in the given constant, we are getting x square plus x square plus x square equal to 1, or we can say 3x square equal to 1, x square is equal to 1 upon 3, or we can say x equal to plus minus 1 upon root 3. In the same way, y equal to plus minus 1 upon root 3, and z equal to plus minus 1 upon root 3. So these are our 3 values through which we are able to find the minimum value. So we have 6 different points. So we can find point 1, point 2, point 3 up to point 8. First point is 1 upon root 3, and or we can say 1 upon root 3. In the same way, 1 upon root 3, and this is 1 upon minus root 3. And in the same way, 1 upon root 3, minus 1 upon root 3, 1 upon root 3. This is 1 upon root 3, minus 1 upon root 3, minus 1 upon root 3. So there are number of points we are getting by solving this one. So when we put this value into this function, what we are getting? We are getting x, y, z equal to, x value is 1 upon root 3, multiply 1 upon root 3, then multiply 1 upon root 3. So we can say 1 upon 3 root 3. It is our maximum value. In the same way, if we are plotting values, that is 1 upon root 3, or we are taking one negative value, then we have minus 1 upon 3 root 3. So this is our second value, or we can say this is our minimum value. So this is how we are getting maximum value, and this is minimum value. So by applying Lagrangian multiply method, we are able to find maximize or minimize value of the given function. So this is, in both examples, we have only one constant. This is x square plus y square equal 1, and this is x square plus y square plus z square equal to 1. So let's learn. In this particular example, we have more than one constant. Let's see what these are. In the third problem, we have given a function that is 2x plus 3y plus 1, and we have given two constants. First constant is x square plus y square equal 5, and second is x plus z is 1. So we have one objective function, that is 2x plus 3y plus 1 plus z. So this is our objective function, and we have two constants, that is x square plus y square plus equal to 5, and second is x plus z equal to 1. That means we have more than one constant, and in previous two problems we have one. Now we are using same method for solving this one. Again, first we need to find how many variables are there in our objective function. So we have three variables, x, y, and z. So we can take this one, x equal 0. These are three. Three values, or we can say three differentiations regarding all these three variables. Now, since it having two different constants, so we have two Lagrangian multiplier constant, that is lambda 1 and lambda 2. So as a solution we have x y z equal to fx y z plus lambda 1 phi 1 plus lambda 2 phi 2. I am using here lambda 1 and lambda 2. These are our Lagrange multiplier constant, or we can say constant, and these are our constant number 1, constant number 2. So this is fx y z equal, we need to find value, that is 2x plus 3y plus z equal lambda 1. Again plotting, taking first constant, that is x square plus y square minus 5 plus lambda 2, that is x plus z minus 1. So as a three values, by taking this first differentiation with respect to x, so taking this one as a 0 and make differentiation of this one, that is 2 for this one, and this is lambda 1 2x, and this is lambda 2 into 1. This is first equation, and in the same way we are applying or taking values by differentiate it with respect to other variables. So taking second one with respect to y, and then with respect to z, and then solve these to get the values of lambda 1 lambda 2, and when we get the value of lambda 1 lambda 2, then we are able to find the values of x, y, z, and then we have 8 different point values. On taking these 8 different point values, we are able to find the optimal solution of this objective function under the given constant. So in these three examples, after getting solution of these three problems, you are able to find the optimal solution of each given function or objective function under a number of constants. Thank you.